Okay guys, welcome back to another video. Today we will take a look at the extended principle of mathematical induction. In the previous video, I introduced you the first principle of mathematical induction, which is a proof for a result or theorem concerning or for positive integer n ranging from 1 through 3 and all the way and so on. The way to prove is that we have to show the base step. Base step in which you have to show that P1 is true, or the case where n equals 1 is true. And the second one is called inductive step. Inductive step, we have to show that pk is true. If pk is true, then pk plus 1 is true for any positive integer n. If you can have the basic step and inductive step, you prove that p of n is true for every positive integer n. This is the first principle of mathematical induction. Sometimes a statement might involve positive integer n such that n greater than or equal to something. For example, maybe n greater than or equal to 2, or maybe n greater than or equal to 5, greater than or equal to 10, and any positive integer a. Okay? So if you want to prove this kind of statement with n greater than or equal to something, we need to use extended principle of mathematical induction. So the way to prove is very similar to the first principle of mathematical induction. So I want you to look at theorem 1.2.3, which is the principle of mathematical induction. So we let Pn be a statement for positive integer n, and a is an integer. Sorry, n is an integer. Okay? If we can show that P of A is true, this one is called base step. If P of A is true, okay, and if you can show that for any integer k, such that k greater than or equal to a, and if pk is true, then pk plus 1 is true. This is inductive step. If you can show that this step is true and inductive step is true, you're going to show that P of n is true for any integer n that is greater than or equal to a. Okay, now we have greater than or equal to a. Okay, unlike the first principle induction, we're going to have just n being positive integer. So let's prove this theorem. Let's prove it. We will use the first principle of mathematical induction to prove it. So the first thing that I want to do is to let n to be an integer such that is greater than or equal to something, let's say a. Okay, for some integer a. Okay, and we let, I think that we have to use just where, okay, not for some, where a is an integer, and then we let Pn be a statement. Let Pn be a statement for positive integer, for an integer n. Okay, and we assume that 1 and 2 are true, because we have to assume this in order to show that P of n is true for positive for integer n greater than or equal to a. So let's assume that one is true and two is also true. So are both true. 1 and 2 are both true. I mean this one and this one, base step and inductive step. So now, since n is an integer such that n greater than or equal to a, okay, where a is an integer. So what do we have right here? So we're gonna have n equal to a, right? Because n greater than or equal to a. So n can be a plus 1, a plus 2, a plus 3, and all the way and so on. Okay, so we want to have an integer start from 1. Okay, 1, 2, 3, and all the way and so on. So I'm gonna let m to be this. I'm gonna let m to be n minus a plus 1 because n start from a. You're gonna have a minus a, m equals 1, and n equals, when n equal to n plus 1, we're gonna have 2. Okay, and when n equal to 2, a plus 2, right, minus a, and 2 plus 1 is 3. So this is what we have. What we have right here is that m will be 1, 2, 3, 4, okay, for n equal to a plus 1, a plus 2, a plus 3, and so on, respectively. Okay? Then, what happened to Pn? The statement that we want to show. Then, Pn is equivalent to Pn will be equivalent to P of m plus a minus 1. Okay? This is n, right? N becomes m plus a minus 1, like this. All right, so what can we do next? So, to show that P of n is true, right? Is true for every integer n such that, how to show it? Such that a greater than, n greater than or equal to a. Okay, we have to show that. We have to show that P of m plus a minus 1 is true for every positive integer m. So we have m start from 1, 2, 3, and all the way and so on, right? Okay, m is 1, 2, 3, and all the way and so on. Okay, so that's what we have right now. We have to show this P of m plus a minus 1 for every positive integer m. So we gotta let Q of m, okay, be equivalent to P of m plus a minus 1, okay, for m for positive integer m. So now m starts from 1 through 3 and all the way and so on. So now we will use the first principle of mathematical induction, okay, to show that Q of m is true for every positive integer m. Okay, we show that Q of m is true for every positive integer m. So we start with base step. Actually, base step. Okay. What is base step? So we have to show that Q1 is true. So we're gonna have Q1, and we know that Q1 is equivalent to P of 1 plus A minus 1, which is PA, right? Which is P of A. Okay? And what did we assume? We assume that 1 is true. And what is 1? 1 is PA is true. So we've just shown that P of A is true, right? Okay, so since the first statement, 1 is true, what do we have? We're going to have that P of A is also true. Therefore, Q1 is true. So we have the base step. Now let's go to inductive step. Let's go to inductive step right here. What do we have to show? We gotta assume that Q of, let's use K, is true. And try to show that Q of K plus 1 is true. Okay? For every positive integer K. So K starts from 1 through 3. Okay? And so on. But QM is equivalent to P of m plus A minus 1. Okay? That's what we know. So since QK is equivalent to this P of K plus A minus 1. But what do we have? QK is true, right? This means that P of K plus A minus 1 is also true. So PK plus A minus 1 is true for every integer K. Now, what should we do? We know that K is a positive integer. So what do we have right here? We're gonna have that K can be a natural number. So K minus 1, what happened? K minus 1 is going to be greater than or equal to 0. And then when we add this A, what happened? We're gonna have K plus A minus 1 greater than or equal to A. Okay? Greater than or equal to A. What does it mean by this? This means that P of K plus A minus 1 is true. For what? For K plus A minus 1 greater than or equal to A. So the variable right here is now greater than or equal to a, because k is greater than or equal to 1. Okay, now what can we do next? So it satisfies the second condition. Oh, sorry, this one. Okay, the second condition, right? So pk is true such that for k greater than or equal to a. So since the second statement is true, okay, I gotta add one more paper. So since the second statement is true, okay, and p of k plus a minus 1 is true for this inequality, okay, for k plus a minus 1 greater than or equal to a, okay. So what do we have here? We're gonna have p of k plus a minus 1 plus 1, or you might write p of k plus 1 plus a minus 1 is true, okay, is true. So k plus 1 is true right now, right? Okay, pk plus 1 plus a minus 1 is true. So this one will be equivalent to qk plus 1. Okay, so since qk plus 1 is equivalent to p of k plus 1 plus a minus 1, what do we have? Q of k plus 1 is true, okay, for every positive integer k. Okay, so the inductive step is true. Therefore, the statement Q of m is also must be true, okay? Is true for every positive integer m, okay? And since statement Qm is equivalent to what? To p of m plus a minus 1. This statement, p of m plus a minus 1, is going to be true for positive integer m. Now what happened to this m? What happened? So we know that m is n minus a plus 1. Okay? Right? Where is it? I lost it. Right here. Okay? So we're gonna have n equals m plus a minus 1. And since m is greater than or equal to 1, we're gonna have 1 plus a minus 1. So we're gonna have just a. Okay? We're gonna have just a, so therefore, we prove that p of n, because m plus a minus 1 is n, so we're gonna have statement Pn is true for every positive integer n such that n greater than or equal to a. That's it. And this is the proof of the extended principle of mathematical induction, okay, in which you have to use this proof to for statement that has n greater than or equal to some positive integer. The examples are here. This one show that 3 raised to the n greater than n cubed is true for positive integer n greater than or equal to 4, and show that this factorial is greater than or equal to 2 raised to the power of n for positive integer n greater than or equal to 4. So in the next video, we're going to prove this example and this example by using the extended principle of mathematical induction. And that's it for today. See you in the next video.